Voyager 2, launched on August 20, 1977 by NASA, stands as one of the most remarkable achievements in human space exploration. Designed to take advantage of a rare planetary alignment occurring once every 176 years, Voyager 2 embarked on a historic grand tour of the outer planets, Jupiter, Saturn, Uranus, and Neptune. This alignment allowed the spacecraft to use gravitational assists to visit multiple planets without expending excessive fuel, a feat that revolutionized our understanding of the solar system. Now, nearly 5 decades later, Voyager 2 continues its journey, transmitting data from beyond the heliopause, the boundary where our solar system meets interstellar space. This extended mission, known as the Voyager Interstellar Mission, VIM, has provided unprecedented insights into the cosmos, making Voyager 2 one of humanity's most enduring scientific endeavors. This comprehensive overview explores Voyager 2's mission, from its inception and planetary encounters to its current role in interstellar exploration. It delves into the spacecraft's design, its scientific discoveries, the challenges of operating a decades-old probe, and the cultural significance of the golden record it carries. While speculative narratives about Voyager 2's findings occasionally capture public imagination, this account focuses on verified scientific data and the mission's profound contributions to our understanding of the universe. In the late 1960s, NASA scientists identified a rare celestial event, a near-perfect alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that occurs once every 176 years. This alignment, occurring in the late 1970s, presented a unique opportunity to send a spacecraft on a grand tour, using gravitational slingshots to visit multiple planets efficiently. By leveraging the gravity of each planet to boost its speed and alter its trajectory, a spacecraft could explore the outer solar system with minimal fuel, a concept that was both ambitious and revolutionary at the time. The Voyager program was born from this vision. Initially proposed as a more extensive mission to explore all 5 outer planets, including Pluto, then considered a planet, budget constraints led NASA to scale back the project to 2 spacecraft, Voyager 1 and Voyager 2, targeting Jupiter and Saturn, with the possibility of extending Voyager 2's mission to Uranus and Neptune. The spacecraft were designed to be robust, capable of operating for years in the harsh environment of space, and equipped with instruments to study planetary atmospheres, magnetic fields, moons, and rings. Voyager 2 was built by NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California. Weighing approximately 815 kilograms, 1,800 pounds, the spacecraft is powered by 3 radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium-238 into electricity. At launch, the RTGs provided about 470 watts of power, though this has steadily decreased over time due to the natural decay of the plutonium. Voyager 2's onboard computer, with a mere 68 kilobytes of memory, was state-of-the-art for the 1970s but is now considered rudimentary compared to modern technology. Despite this, the spacecraft's design has proven remarkably resilient, allowing it to operate far beyond its original mission parameters. 2 cameras for capturing high-resolution images of planets and moons, for studying planetary atmospheres and stellar radiation, to measure thermal emissions and atmospheric composition, for detecting radio emissions from planets, to study charged particles in planetary magnetospheres and the solar wind, for measuring cosmic rays and charged particles, to study planetary and interplanetary magnetic fields, for detecting high-energy particles from the Sun and beyond. These instruments, combined with a high-gain antenna for communication with Earth, enabled Voyager 2 to collect a wealth of data during its planetary flybys and beyond. Voyager 2 reached Jupiter on July 9, 1979, following its twin, Voyager 1, which had passed the planet 4 months earlier. The spacecraft's flyby revealed Jupiter's dynamic atmosphere, characterized by swirling cloud bands and the massive Great Red Spot, a storm larger than Earth. Voyager 2's cameras captured detailed images of Jupiter's moons, particularly Io, where it confirmed active volcanism, a groundbreaking discovery that marked the first observation of volcanic activity beyond Earth. The spacecraft also studied Jupiter's magnetic field, which is the strongest in the solar system and detected intense radiation belts that pose challenges to the spacecraft's electronics. High-resolution images of the planet's cloud patterns and storms. Evidence of a faint ring system previously unknown. Detailed observations of moons like Europa, Ganymede, and Callisto, revealing diverse geological features. On August 25, 1981, Voyager 2 made its closest approach to Saturn, capturing stunning images of the planet's iconic ring system and its largest moon, Titan. The rings, composed of countless particles of ice and rock, were revealed to have intricate structures, including gaps and divisions caused by gravitational interactions with Saturn's moons. Titan's thick, smoggy atmosphere, rich in methane, hinted at the possibility of liquid on its surface, a hypothesis later confirmed by the Cassini mission. Voyager 2's trajectory was adjusted during the Saturn flyby to send it toward Uranus, a decision that committed the spacecraft to the extended Grand Tour. Complex ring structures, including the discovery of new ringlets. Atmospheric data showing high-speed winds and storms. Observations of moons like Enceladus, which appeared unusually reflective, suggesting an icy surface. Voyager 2's encounter with Uranus on January 24, 1986, was a historic milestone, as it was the first and only spacecraft to visit this distant ice giant. Uranus presented a strikingly bland appearance, with a featureless, pale blue-green atmosphere due to methane absorption. However, Voyager 2 revealed a planet with a peculiar magnetic field, tilted 59 degrees relative to its rotational axis, suggesting a complex internal structure. The spacecraft also discovered 10 new moons and a faint ring system, expanding our understanding of Uranus's system. A highly tilted magnetic field, possibly due to a subsurface ocean. Observations of moons like Miranda, which displayed dramatic geological features, including cliffs and fault lines. Data on Uranus's atmosphere, revealing extreme cold and high winds. On August 25, 1989, Voyager 2 reached Neptune, completing its planetary tour. The spacecraft revealed a vibrant blue planet with dynamic weather patterns, including the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot. Neptune's atmosphere exhibited the fastest winds in the solar system, reaching speeds of up to 2,400 kilometers per hour, 1,500 miles per hour. Voyager 2 also studied Neptune's largest moon, Triton, which showed evidence of cryovolcanism, volcanic activity involving ice rather than molten rock. The Great Dark Spot and other atmospheric storms. A faint ring system with arcs of denser material. Triton's nitrogen geysers and thin atmosphere, making it one of the most geologically active moons in the solar system. After the Neptune flyby, Voyager 2's primary mission concluded, and its cameras were powered down to conserve energy. The spacecraft was now on a trajectory that would carry it out of the solar system into the uncharted realm of interstellar space. After completing its planetary encounters, Voyager 2 began the Voyager Interstellar Mission, VIM, with the goal of studying the outer boundaries of the solar system and the interstellar medium beyond. On November 5, 2018, Voyager 2 crossed the heliopause, the boundary where the solar wind is overtaken by interstellar particles and magnetic fields. This marked the spacecraft as the second human-made object, after Voyager 1 in 2012, to enter interstellar space. The heliopause is a dynamic region, shaped by the interaction between the solar wind, a stream of charged particles from the Sun, and the interstellar medium, which consists of cosmic rays, neutral atoms, and magnetic fields from the galaxy. Voyager 2's crossing provided a unique opportunity to study this boundary, as several of its instruments, particularly the Plasma Science (PLS) experiment, remained operational, unlike those on Voyager 1. Voyager 2's data from interstellar space has revealed a complex and dynamic environment. Scientists expected the interstellar medium to be relatively uniform, but Voyager 2 detected unexpected variations. The spacecraft observed higher-than-expected plasma densities in some regions, suggesting that the interstellar medium is not as homogeneous as models predicted. Voyager 2 detected bursts of high-energy particles, indicating interactions between the solar system's boundary and galactic cosmic rays. The spacecraft measured shifts in magnetic field orientation, providing clues about the structure of the interstellar medium. These findings have challenged existing models of the heliosphere and its interaction with the galaxy. For example, the boundary region appears to be more turbulent than anticipated, with complex interactions between solar and interstellar particles. Voyager 2's data has also provided a rare opportunity to compare conditions at two different points in interstellar space, as its trajectory differs from Voyager 1's. Operating Voyager 2 in 2025 presents significant challenges. The spacecraft's RTGs now produce less than 200 watts of power, requiring NASA to carefully manage which instruments remain active. Communication with Earth, facilitated by the Deep Space Network, DSN, is slow, with signals taking over 18 hours to travel the 19.9 billion kilometers, 12.4 billion miles, to Earth. The spacecraft's aging hardware occasionally causes glitches, such as misaligned antennas or temporary data interruptions, which engineers must address remotely. Despite these challenges, Voyager 2 continues to transmit valuable data. NASA estimates that the spacecraft may remain operational into the late 2020s or early 2030s, depending on power levels. When power becomes insufficient to operate scientific instruments, Voyager 2 will cease transmitting data, though it will continue drifting through space, carrying its golden record into the cosmic void. One of Voyager 2's most enduring legacies is the Golden Record, a 12-inch gold-plated disc attached to the spacecraft's exterior. Conceived by a team led by astronomer Carl Sagan, the record is a time capsule designed to communicate the story of humanity to any extraterrestrial civilization that might encounter it. The record contains natural sounds like wind, rain, and animal calls, as well as human sounds like footsteps and laughter. A diverse selection, including Beethoven's Fifth Symphony, Chuck Berry's Johnny B. Good, and traditional music from cultures worldwide. Spoken messages in 55 languages, from Akkadian to modern English. 116 encoded images depicting Earth's landscapes, people, and scientific achievements. A map showing Earth's location relative to 14 pulsars, allowing potential finders to trace the spacecraft's origin. The Golden Record is both a scientific and cultural artifact, symbolizing humanity's curiosity and desire to connect with the unknown. While the odds of an extraterrestrial civilization finding the record are vanishingly small, it serves as a poignant reminder of our place in the cosmos. As Sagan described it, a bottle cast into the cosmic ocean. In recent years, speculative claims about Voyager 2's findings have circulated, particularly on social media platforms like X. These narratives often suggest that the spacecraft has detected anomalous signals, evidence of extraterrestrial intelligence, or phenomena that defy known physics. Such claims typically cite unexplained data bursts, alleged changes in transmission frequency, or supposed interventions by external forces. However, these stories lack credible evidence and are not supported by NASA or the scientific community. Voyager 2's data is rigorously analyzed by scientists at JPL and other institutions. Anomalies, when they occur, are typically attributed to the spacecraft's aging systems, including its RTGs and onboard computer, can cause intermittent glitches. High-energy particles or magnetic fields in interstellar space can disrupt data transmission. The vast distance and weak signal strength can lead to errors in data reception. For example, in 2023, Voyager 2 temporarily lost contact with Earth when its antenna was misaligned, requiring NASA to use a powerful DSN signal to reestablish communication. Such events are often misinterpreted as evidence of extraordinary phenomena, but they reflect the challenges of operating a 48-year-old spacecraft. NASA maintains transparency about Voyager 2's status, regularly publishing updates on its website and through scientific papers. Claims of suppressed discoveries or involvement by intelligence agencies are speculative and lack substantiation. The scientific community continues to interpret Voyager 2's data within the framework of established physics, focusing on its contributions to our understanding of the interstellar medium. Voyager 2's mission has profoundly shaped planetary science and astrophysics. The spacecraft revealed the unique characteristics of the outer planets and their moons, from Io's volcanism to Triton's cryovolcanism. Its interstellar data has refined models of the heliosphere and its interaction with the galaxy. Voyager 2's longevity demonstrates the durability of its design, informing future deep space missions. The mission's data continues to be studied, with new analyses yielding insights decades after the original observations. For example, Voyager 2's plasma measurements have